Continuing on in section 4.2, we can describe the relationship in problem 1 by saying that the perimeter is a function of the number of rectangles. A function is a relationship that pairs each input value with exactly one output value. So 2 rectangles gave us exactly 1 perimeter. 10 rectangles would give us exactly 1 perimeter. We've seen that one way to represent a function is with a graph. A linear function is a function whose graph is a non-vertical line or part of a non-vertical line. So a linear function is a line. Okay, it can't be straight up and down, but it can be left to right, going up, going down. It can be just the dots like we did in our perimeter and our triangle. It can maybe go just one way. That's fine as well. It just can't be straight up and down, and it has to be a line in that we can connect it with a straight edge. So it can't be curvy, has to be a line. Example 2 is representing a linear function. The table on the top of page 242 shows the relationship between the number of photos X you make and the amount of memory Y in megabytes left on your camera's memory chip. Is the relationship a linear function? Describe the relationship using words, an equation, and a graph. So here, in order for it to be a linear function, the ratio of the change of our outputs has to match every outputs to inputs matches every time. So if we look here, we go up 1, here we go up 1, here we go up 1, here I go down 3, down 3, down 3. So when I take the ratio of those, -3 to 1 gives me -3. -3 to 1 gives me -3. And -3 to 1 gives me -3. So the ratio of my outputs to inputs is the same every time, which means yes, it is linear. Now it wants us to describe the relationship using words, an equation, and a graph. And again, there's lots of different ways that we can write this in words. Here I just said where we started. So we start off with 512 megabytes. And for every picture we take, the megabytes left in memory goes down by 3. And again, what you came up with might have been different, and that's okay. Now we need an equation. So we got to figure out what's happening here. Well, we started off with 512 with 0 pictures. And if we take 1 picture, we still have that same like memory card or storage amount, and we subtracted 3 from it. For 2 pictures, we still started off with the same amount. The first picture took away 3, the second picture took away 3. And for 3 pictures, we started at the same amount. We took away 3 for the first picture, 3 for the second picture, 3 for the third picture. So the amount that stays the same every time is our 512. And again, that's what we started off with. So remember, our memory is Y, that's our output. X is our number of pictures, that's our input. And here we have 512, so I'm going to add 512. And what's changing every time is we subtract 3. So for 1 picture, we subtracted it 1 time. For 2 pictures, we subtracted it twice. For 3 pictures, we subtracted it 3 times. So we take our number of pictures times that -3. So it's either -3x plus 512, or you can say 512 and then we subtracted 3 times. So it also could have been 512 minus 3 megabytes for each picture. Either one of those would work. They're essentially the same thing because we can add in any order. And a graph. So our input is our X value. It goes on the bottom. Input always goes on the bottom. And here, that is our number of photos. And here we go up by 1. So again, my corner is 0, 1, 2, 3, 4, and so on. If we look at my megabytes left though, my memory, which goes on my side, because it's my dependent output, here we're all the way at 512 and we go to 503. So what I'm going to do is I'm going to use a broken graph. We put this little zigzag here to tell, hey, there's some things in the middle there, there's just nothing going on there. So I can start at 500. And because I put that broken graph symbol there, I don't have to go by 500s every time. That's a new starting point, and we only do that on the y-axis, but we can do that when our values are pretty far away. So then I can go by 2s or by 3s or whatever you want. If I go by 3 here, though, I have to keep going by 3. We can only use that broken graph once. And again, anytime you change your scale other than 1, you need to have it labeled. And I don't even need to go any further than 512 because that's the most that we have. So as far as graphing this goes, with 0 pictures, we had 512. With 1, we had 509. With 2, 506. 3, 503. With 4, if we subtracted 3 again, we'd be at 500. So we can't connect these because I can't take half of a picture. I can't have 2.5 pictures, but I can put an arrow to say that this pattern continues. It won't continue forever. Eventually we'll get to a number of pictures that has used all of our storage, but it will go for quite a ways. We can go all the way down to 0 for that storage, so we can put an arrow there. Now, it says, is the relationship in the table on the bottom of page 242 a linear function? Describe the relationship in words, an equation, and a graph. So if we look here, I go up by 1, I go up by 1, I go up by 1. Here I go up by 2, I go up by 2, I go up by 2. So my ratio of outputs to inputs is 2 over 1, 2 over 1, and 2 over 1. So since my ratio of outputs to inputs is the same every time, yes, it is linear and a function. Now we can describe the relationship in words, an equation, and a graph. And remember, in words, there's a lot of different ways that we can write this. Here I said, starting at 8, we increase by 2 every time. So we can take 2 times our input and add 8 to get our output. So instead of continuing that pattern every time, if we wanted to get to an input of 100, let's say, that would be a pattern we could use. So as far as an equation goes, here at 0 I have 8, and then I increased and I got up to 10. And then I had 2 increases from that 8 to get to my 12. To get to my 14, I increased to get to 10, and increased to get to 12, and increased to get to 14. So my output y is 8. That stays the same every time. And then we added, and when my input was 1, I added 1 2. For an input of 2, I added 2 2s. For an input of 3, I added 3 2s. So I can take my input x times 2. So 2 times my input, 3 or 2 or 1, plus 8 gives me my equation. And a graph. So here, my input is just x. And here we go, 0, 1, 2, 3. My output is my y, and it's 8, 10, 12, 14. So I can either go by 1s here or by 2s. I'm going to go by 2s. So 0, 8, 1, 10, 2, 12, 3, 14. And because we don't have a situation for this table, there's nothing else we can do there. I can't say, hey, this pattern continues, because we don't know if it does or not. We know that we can add more rectangles or add more triangles or take more pictures. But here we don't know what this situation is. This could be the only data we have. So we leave it just like that. Now we want to know, does the set of ordered pairs here represent a linear function? Why or why not? Here it does not. And we have a couple different ways that we can tell. First way we can tell is because one input gives us 2 different outputs. So for example, if I have one rectangle, I can't get 8 as a perimeter and 4 as a perimeter. So, one input cannot give two different outputs. The other way we can tell here is if we try and figure out our change between them. So even if we just use the points 0, 2, 1, 4, and 3, 5, and forget about that 1, 8. Here, my change in x's is 1. Again, from 0 to 1 is 1, and from 1 to 3 is 2. From 2 to 4 is up 2, and from 4 to 5 is up 1. So if we look here, and I find the ratio of them, 2 over 1 gives me 2, but 1 over 2 gives me a half. 2 does not equal a half, which means my change isn't the same. If we were to graph these, 0, 2, 1, 4, 3, 5, they wouldn't be in a straight line, so it's non-linear. So our ratios of changes is not the same. Quick recap, the value of one variable may be uniquely determined by the value of another, and such relationships may be represented using words, tables, equations, sets of ordered pairs, and graphs. And that's all for section 4.2.